Okay, so we're at the second day of the Black Hole Microstructure Conference, and we're delighted to have Matthias Gaberdiel, who's going to talk about the exact ADS-CFT and exact ADS-CFT duality. Over to you, Matthias, and thank you.
Okay, well, thank you very much, and thanks very much for the invitation. So I'm going to describe some work I've been doing mainly with Rajesh Gopakuma and Lawrence Eberhardt, but also more recently with my more recent PhD students, Andrea Day and Bob Knighton. So okay. So it's been long suspected that the CFT dual of string theory on ADS3 cross S3 cross T4 is on the same moduli space of CFTs that also contains the symmetric orbifold theory. So this is part of common knowledge, and so we all know this very well. But what wasn't known until recently, or what we claim now to have understood, is how specific points on the two moduli spaces are related to one another. So in particular, there's on the CFT moduli space, there's one preferred point, which is the symmetric orbifold theory itself. That's the theory which David Turton was talking about yesterday. And on the string moduli space, on the string theories describing strings on ADS3, process 3 plus T4, say, there's a preferred line corresponding to the situation where you have an exactly solvable worldsheet theory described by a Wessel-Miller-Witten model. So this is the background with pure Navier-Schwarz flux. So you know that the whole moduli spaces should map to one another. You have a preferred line here, and you have a special point here. But one didn't know really how these two points, how these two special lines or points are related to one another. Now, in fact, the only consensus was that this point can't possibly lie anywhere on this blue line. So there's a line here because you have a level, and here there's just one point. And the consensus was that this point is definitely not lying on any point of this line. And the basic reason for that is that the Wessel-Miller-Witten model describes the background with pure Navier-Schwarz flux through the ADS3 factor. And that's known to have these so-called long string solutions. These are string solutions that live close to the boundary of ADS. And because they live near the boundary of ADS, the excitation spectrum is redshifted. And as a consequence, they give rise to a continuum of excitations. So the space of states for this Wessel-Miller-Witten pure Navier-Schwarz flux backgrounds should be continuous. But on the other hand, the symmetric orbifold of T4 is not doesn't have a continuous spectrum. It has a discrete spectrum. So clearly, these two things can't be exactly dual to one another. That was sort of the consensus view. Now, as we noticed some years ago, the symmetric orbifold theory is quite special. I guess that's what many people knew. But what we noticed, or what we realized, was that it actually has what's called a W infinity symmetry algebra inside it. And that's believed to be a hallmark of being dual to a massless higher spin theory in ADS3. So from the point of view of the dual CFT, you see lots of chiral fields, and they should correspond to massless higher spin fields in the bulk. And the usual picture is that that should happen only near the tensionless point of string theory in ADS3. So what it suggests is that a symmetric orbifold theory should be dual to string theory at a tensionless point. Now, the tensionless point means that the string is has a small tension, is very large. So it means that the string is as large as the space-time geometry in which it propagates. This is the deeply stringy regime. So this is the total opposite of the supergravity regime. This is the regime where the string is very large rather than being almost point-like like in supergravity. And if you believe that maybe it has something to do with this Wessel-Miller-Witten model description, the deeply stringy regime, the regime where the string becomes tensionless, is related to the situation where the level of this SL2R Wessel-Miller-Witten model takes the smallest possible value. Because the level is a measure for the size of the ADS3 space in units of the string length. And therefore, a tensionless string means that the space is as small as the string, or the string is as large as the space, which means K, this level, should take the smallest value, which you may believe should be equal to 1. So this led us to study the space-time spectrum of the K equals to 1 SL2R Wessel-Miller-Witten model systematically. This is something one could have, in some sense, done already many years ago. And upon analyzing it carefully and looking at the right degrees of freedom, and I'll explain to you a little bit in the following exactly what we did, we found extremely good evidence that this level 1 Wessel-Miller-Witten model is exactly dual to the symmetric orbifold theory, to this special point. So that the picture alluded to before is that the special point on the CFT moduli space corresponds exactly to one point along this blue line of pure Navier-Schwarz backgrounds, namely the point where the level is smallest, i.e. the size of the space is as small as it's allowed. And what my talk is about, to explain to you what evidence we have for this claim that these two theories are exactly the same. So the statement is that the string theory described by this solvable worldsheet theory has a space-time spectrum that's exactly described by the symmetric orbifold theory in the large N limit. So it's not just the BPS spectrum, it's the full spectrum of states. It reproduces the full spectrum of states here, and correlation functions here are being reproduced by correlation functions in the worldsheet theory here. So this is going to be the bulk of my talk. Towards the end of my talk, I also want to explain to you some very recent work that happened about a month ago. Namely, we've understood how to reconstruct the worldsheet theory from the dual CFT. Now, in some sense, you may think this is superseded by the fact that we can show this directly. Excuse me. But in order to see how this ADS-CFT duality in 3 dimensions fits into the more general story, it's interesting to see whether we could have guessed what the worldsheet theory is without going via the route we've gone through. And what we've observed, and I'll explain to you in more detail how this goes, is that in the large twist limit, the symmetric orbifold correlators can be very naturally rewritten in terms of an integral over string moduli space, and along very much the lines that Rajesh-Gopakuma proposed many, many years ago for how one could reconstruct the worldsheet theory of the dual CFT. And while in some sense this is superfluous because we have already this exact description, what it shows is that this fits into this more general framework very nicely, and therefore gives you hope that maybe this duality is not that dissimilar to what will happen, say, for ADS5. So this gives us hope that maybe by similar techniques, we may be able to find an exact description of the worldsheet theory that's dual to, say, 3 supereminence.
Matthias, a small question, please.
Yes.
Samir here. So
Yes.
I was just wondering, do you need to have one of these flat connections turned on in the T4, which will then prevent the long string from being able to come out to infinity? Would you turn on some of these constant B modes?
But maybe you ask again later after you've seen how it works.
Okay.
As the T4 really just goes along for the ride. There's nothing special happening along the T4.
Okay.
But you'll see. Maybe we can come back to this later on.
Sure.
Okay, so this was my brief introduction and motivation. And so what I want to do is I want to first explain to you how we go from this explicit worldsheet description that we propose to the dual CFT, and how you reconstruct, recover the spectrum, and how you recover the correlators of the dual CFT. And then I want to show you how you can go the opposite way, how starting from the symmetric orbifold CFT, you can reconstruct how the string theory must look like, at least in this large twist limit. And then I'll conclude with some more general comments. Okay, so let's start with showing you how to produce the spectrum of the dual CFT from this worldsheet description. Now, as some of you, I'm sure, know very well, and I'm glad I wasn't yet interrupted, is that the k=1 theory is a little bit delicate, as many of you know. In particular, if you try to describe this in the NSR formalism, this leads to a problem because the SU2 factor seems to have a negative level, and there are all sorts of funny things happening. Now, what we are going to do is we are going to use an alternative description of string theory and ADS3 × S3, which is known as the so-called hybrid formalism and goes back to Berkowitz, Buffer, and Witten. So this was invented as a way of not just being able to describe pure Navier-Schwarz flux, but also being able to switch on Ramond flux. But you may as well just study it for the case for pure Navier-Schwarz flux, in which case it amounts to considering a Wessel-Witten model based on the super Lie algebra PSU1,1/2 at level k, together with some topologically twisted sigma model for T4. And for generic k, this description was shown in a variety of papers to reproduce exactly what's known from the Maldacena-Oguri NSR sector description. So it's a good belief to say that this describes string theory in ADS3 × S3 with k units of Navier-Schwarz flux, if you just take this background to start with. So we're going to take this theory, and in this formulation, there doesn't seem to be anything particularly wrong with setting the level k equals to 1, unlike the NSR description of Lamaldesino-Ogori. So what we're going to do is we're going to use this formalism and work with the super Lie algebra at level 1 and understand what the spectrum looks like. Now, what's important, what's really the key idea in this is to seriously look at the representation theory of the super affine Kac-Moody algebra. So this sounds maybe a little bit complicated, but actually the key idea one can really understand based on rather simple observations. So this PSU1,1/2 super Lie algebra has as its bosonic Lie algebra SL2, which is basically SU1,1 and SU2 coming from the second half here as bosonic subalgebras, and they're both sitting at level 1 if the PSU1,1/2 theory sits at level 1. So this is just the bosonic subalgebra. So if you look at the highest rate representation of this super Lie algebra, in particular, it must be an allowed highest rate representation of SL2 level 1 and SU2 level 1. This is just follows from the fact that this is a part of the constraints that come from there. So in particular, it must be an SU2 level 1 highest rate representation. But as many of you probably know, SU2 at level 1 has only 2 allowed highest rate representations, namely the representation corresponding to j equal to 0, the one-dimensional representation, and the two-dimensional representation, the j equals to a half representation. As you may know, SU2 level k has spins up to level k over 2. So for k equals to 1, you go up to spin a half. So you have 2 possible highest rate representations for SU2 level 1. Now, if you look at, now here we have this super Lie algebra. So you can ask, suppose we have some highest rate representation of this affine Kac-Moody algebra. It must be in particular form a representation of the zero modes, I of the global super Lie algebra PSU1,1/2. Now, what does a generic representation of this PSU1,1/2 algebra look like? Well, I mean, it's a super Lie algebra, so it has fermionic generator, so it has this sort of Clifford algebra type, Clifford representation type structure. You start with some representation of SL2R, which I take to be a continuous representation, and some representation of SU2, which I label by its dimension. So n is just the dimension of the SU2 representation that sits here. And then I have 4 supercharges, and I can apply them once or twice or 3 times and 4 times. And I map out this whole set of representations. And because the supercharges sit in the doublet with respect to SL2 and the doublet with respect to SU2, they move the SU2 label up by 1 and down by 1, and the SL2 label up by a half and down by a half. So this is just standard representation theory for how these sort of super Lie algebra representations look like. So that's a generic representation of the zero mode algebra, a long representation. And if you look at it, I mean, you just have to spot that if you have n here, you have going to be n plus 2 here. I mean, this is just a fact of representation theory of the super Lie algebra. But remember, I told you that the SU2 algebra is only allowed to have n equals to 1 and n equals to 2 as highest rate representation. And therefore, a long representation is incompatible with the SU2 level 1 symmetry, because you're going, even if you take this to be 1, you'll have a 3 here, and 3 is not allowed for SU2 level 1. So what this tells you is that the long representations are not allowed representations of PSU1,1/2 level 1, simply following from the representation theory of the SU2 level 1 subalgebra. So you can study which representations of PSU1,1/2 are allowed, and what you find is actually only one representation that's possible, namely an ultra short representation that just consists of 3 factors. I mean, again, this is an SL2 representation, this is an SU2 representation, and similarly for the others. But then when you study the conditions, so this is a short representation, or short representations don't generically exist. They only exist if the quantum numbers take specific values. And what you find is that the shortening condition is only possible. It actually implies that J, the spin of the SU2 representation, must actually be equal to a half. So instead of having this continuous representation, the only representation that's possible is that it's at the bottom of the continuum, i.e. that S is equal to 0. So instead of having this usual continuum you see for this Resumino-Witten model type string theories, the continuum has disappeared, but it's a fact of this true quantum nature of this background, of the fact that this super Lie algebra representation theory is very tight, that forbids any of the continuous part of the spectrum, and therefore removes this obstacle towards it being possibly dual to the symmetric orbifold. Because I didn't explain this, but this parameter S, which can take a continuous value, is responsible for the continuous spectrum of this Wessel-Newton theory. So,
Matthias?
yes.
That's actually a little confusing. So in a lot of the work on SL2 current algebra, usually this representation is thrown out because it's not normalizable.
Right. So you may be worried about normalizability, but here we are just, so normalizability is something which you think of in terms of the Peter-Weyl theorem on the group, in terms of a geometric, quasi-geometric analysis. Here we are just doing the representation theory of the super Lie algebra. And what we are finding is it has only one representation. Well, actually, there's a one parameter family of representations labeled by this parameter alpha, which gives you the J30 value mod Z. But basically, there is only one representation. And I think this is a consistent CFT. Now, its geometric relation to normalizable wave functions on ADS3 may be delicate, but I think we are in a regime where this is a difficult thing to ask because we are very far from geometry.
Right, but I mean, if you just look at things like the correlation functions for which, the exact algebraic expressions are known, if I'm remembering correctly, we have a pole at this value of J.
Well, I'll come to correlation functions later on, but what I claim is that the worldsheet theory that takes this super Lie algebra, which I claim is the legitimate description of ADS3 at level 1, has this property that that's its only representation, and I'll give very good evidence that it defines for you a consistent worldsheet theory, and I'll show that its spectrum reproduces that of the symmetric orbifold of T4. So, you may not think that this has anything to do with ADS3, but I think this is a legitimate worldsheet theory that ticks all the boxes that you may ask to be ticked. And as I'll try to explain in the rest of my talk, it actually seems to work perfectly.
And maybe this is tied to the fact that you're not allowing continuous values of J.
It's not that I'm not allowing it. It's forced upon me by the representation theory of this super Lie algebra.
Right. But I think that the theorems I'm quoting, or the results I'm quoting, have to do with writing down a result for general J and then continuing it.
General K. You're thinking of it in the large K limit, right? Where you can think of it in terms of wave functions on ADS3.
No. There's just a general expression for the SL2 correlation functions for general K and J in terms of ratios of gamma functions, say for the 2-point function.
Right.
And that function just happens to have a pole at K equals at J equals a half.
Well, as you will see, we'll be calculating correlation functions, and the correlation functions of the theory are perfectly fine. And in fact, they reproduce exactly those of the symmetric orbifold of T4. Now, they're a little bit different than the ones you probably have in mind, and I'll explain later on what's the correct way of calculating correlation functions in this theory.
Okay.
So maybe we can come back to that later.
Okay, great.
So this is a very special representation, and it's if you look at it, it's really, if you look at its partition function, it has lots of null vectors. It's very far away from the typical representation you would have in mind. So if you think about it, TSU1,1 has 6 bosonic generators and 8 fermionic generators. So you would have expected that if you remove the ghost, you will have 4 bosonic generators left over because you have 6 to start with, 3 from here and 3 from here, and the ghosts eat 2. So you would have thought that the partition function should basically go like 1 over eta to the 4. Now, in fact, this representation is zillions of null vectors, and the moral analog you should think of is that it behaves very much like SU2 at level 1. You see, SU2 at level k, the character goes like 1 over eta cubed because it has 3 bosons, 3 bosonic degrees of freedom for a 3-dimensional space. But SU2 at level 1, as many of you will probably know, is really equivalent to the theory on the circle. So its character really goes like 1 over eta. And here, roughly speaking, you get the same phenomenon type happening for SL2. So instead of having 3 bosonic degrees of freedom from here, you've only got 1. Instead of 3 coming from here, you've only got 1. So the generic representation is only 2 bosonic oscillating degrees of freedom, and then the ghosts remove all the oscillating degrees of freedom, and what you're left over with after you've removed the ghosts are just zero modes. So this is again super special for this sitting at level 1. It just means that this theory has far fewer degrees of freedom than you would have thought. Now, once you take the zero modes and you combine it with the T4 and you impose the mass shell condition, what you find is that every state from the T4, every state you can write down survives because the mass shell condition picks up exactly one term out of this infinite sum. So the mass shell condition you solve by picking out the right zero mode contribution from ADS3 plus S3. And if you go through it and you calculate it, what you find is that for all the degrees of freedom of T4, an excitation survived. And they have, in fact, this is a very non-trivial calculation, but I don't have the time to show it. You get exactly the correct conformal dimensions for the states UTAT from the point of view of the space-time CFT. So this reproduces exactly on the nose the single particle spectrum of the symmetric orbifold of T4 in the larger limit. So you combine this PSU1,1/2 level 1 with the T4, you impose the mass shell condition, you remove the ghost and so on, and out pops, if you just study the space-time spectrum, the space-time spectrum of the single particle part of the symmetric orbifold of T4. Where by single particle, I mean single cycle in the same sense that David Turton was explaining yesterday. So this explains to you how the spectrum emerges from this very specific worldsheet theory. So this is a very specific worldsheet theory, has very special properties. In particular, instead of having 8 oscillating degrees of freedom, it really has only 4, and that matches with the 4 oscillating degrees of freedom you see in the symmetric orbifold of T4. Now, how about correlators? If you want to see that two theories are the same, you should show that the spectrum is the same, but you should also reproduce the correlators from the worldsheet. Now, so let's remind ourselves what the symmetric orbifold roughly looks like. So this is similar to what David was saying yesterday. So we have an untwisted sector. So you have four free bosons, 4 free fermions from here. You take n copies, you make them invariant under the symmetric group. You have an untwisted sector, and then you have twisted sectors, and they are associated to the conjugacy classes of Sn. The conjugacy classes are labeled by cycle shapes, i.e. partitions of n, and we are going to concentrate on the single cycle sectors, which are the analog of the single trace states. And in particular, I didn't really explain this, but if you go through it, the W cycle twisted sector is exactly what comes from spectral flow equals to W on the worldsheet. So that's exactly how this correspondence works out.
What was the parameter n on the gravity side?
So n is going to be taken to be large. And as you'll see, the string coupling constant will be proportional to 1 over square root of n.
Okay.
But I should say this clear, we are always taking the n goes to infinity limit. So we're always working in the larger n limit. But as I'll try to explain to you, our results seem to also reproduce correctly all 1 over n corrections. But we're not working at finite n, we are taking n to infinity, but then we are contemplating including all 1 over n corrections, which is obviously different than working at finite n. So we don't have a proposal for finite n, but we have a proposal for the n goes to infinity limit, including all 1 over n corrections.
So just to follow up, so n has nothing to do with any flux. I mean, k equals 1 is your 1 unit of Neveu-Schwarz flux, but n has no flux interpretation in this.
No.
Okay, thank you.
Okay, so how do you calculate correlation functions in the symmetric orbifold theory? So the basic correlators we're going to be interested in are correlators associated to these twist fields. So twist fields of a twist W. And the way to calculate these correlation functions is to go to the covering map. So what's the effect locally of a W cycle twist field? Well, it means that if you take one of our free bosons and free fermions and you go around the twist field, it gets permuted by the W cycle permutation. So you have to go around W many times before you come back to itself. So what this means is that near a twist field, locally, if you want to have single-valued correlation functions for the individual n free bosons and fermions, you must introduce a W-fold cover. You must introduce a multi-story car park of W covers that has the property that if you reach the top level and you go further up to the top, you get back to the bottom. That's what I mean by W multi-story car park. So this is what the world looks like near each of these twist fields. And then the idea is that if you calculate a correlation function of n such twist fields say, on the sphere, then locally you do this covering map, and then you are trying to glue together this covering map, this local covering map, in such a way that you get a global covering map. That is a map from some Riemann surface that maps down to the sphere on which we are calculating the correlation functions, and that has the property that near each of these twist fields, it looks exactly like such a W-cycled multi-story car park. And the conformal map, the covering map, is then simply the analytic map from this complicated Riemann surface down to the sphere that has this property that locally it looks like this W-story car park. Now, if you want to calculate correlation functions of the symmetric orbifold on the sphere, and in particular, if you concentrate on the ground states of the twisted sector, then you see once you've gone the ground state of the twisted sector, their only purpose in life is to make sure that you have this property that as you go around, you change identity of the fields until they've come back to themselves. So once you've lifted them to the covering surface, these fields have disappeared entirely from the description. So what this means is that in terms of this covering surface, you're just looking at a vacuum correlator, which is equal to 1. So what this means is, and this is an idea that was pioneered by Lunin and Matur, is that the correlation functions of this twisted sector of the symmetric orbifold for the twisted sector ground states is basically just described by the holomorphic map to the covering space and by the conformal factor that you pick up from this holomorphic map. So the way you calculate this is you just find this covering map, and then you evaluate the Liouville term so the gamma is the covering map. You take the derivative of gamma, you calculate the Liouville field, you plug it into Liouville action. That gives you the conformal factor that's associated to this conformal transformation from your base space to the covering surface. And since on the covering surface the correlator is unity, that's all the correlator on the base space is. And Lunin and Matur showed that this reproduces correctly symmetric orbifold correlators as you expect them to be. Now, as I haven't said explicitly, but you see, we are interested in correlation functions on the sphere, but the covering map needn't be a sphere. In fact, in general, the covering map will have a genus, and the genus captures the leading order in 1 over n, the 1 over n behavior of the correctly normalized single trace operators of the correlators on the sphere. So if you calculate the correlation functions of n single trace operators, then the 1 over n behavior to leading order is captured by the genus of this covering surface. And so the idea is that this genus, so the idea is that the string coupling constant of the dual string theory should be related to 1 over square root of n, and therefore this behavior reminds us of how the worldsheet higher genus contributions should contribute to such correlation function, and therefore it suggests that we should think of the covering surface as being the worldsheet. So this was a proposal that was made very explicit in this paper of Pachman, Rastelli, and Razamat in 2009. They proposed that, thought about it in this way. What it suggests is that the covering surface that appears naturally in the calculation of the symmetric orbifold correlation function should be thought of as being the worldsheet of the dual string. And then the genus expansion reproduces correctly the 1 over n expansion of all of these correlation functions. Now, while at this stage this was a nice idea, now we are actually in a position to check it, because we have a concrete worldsheet theory that's meant to reproduce this. I mean, we know exactly which worldsheet operator corresponds to a twisted sector ground state, so we should see whether the correlation functions on the worldsheet have the property that they reproduce this covering space picture. Now, the construction of the vertex operators on the worldsheet is a little bit subtle and is a bit different than what people had done before. So the idea is that, so you identify states and fields at one point, but we introduce 2 variables for these worldsheet operators, namely one that describes the usual coordinate on the worldsheet, that's the z coordinate. And the z coordinate is related to the origin simply by translation in the z with the translation operator on the worldsheet. But likewise, we can introduce a variable x that describes the position in the dual CFT. And that position is translated from its position 0 by the translation operator of the dual CFT. But the translation operator of the dual CFT, i.e. L-1 CFT, is just j plus 0, the 0 mode of one of the 0 modes of the SL2R Wessel-Witten model. So therefore, what we propose is we introduce vertex operators that depend on x and z where the x and z dependence is just induced by the usual translation with the translation operator on the worldsheet and the translation operator in the dual CFT. And luckily enough, J0 plus an L minus 1 commute. So this is totally unambiguous what you mean by this worldsheet operator. So what we are proposing is we should calculate these, the correlation functions of these vertex operators and see whether we reproduce what the symmetric orbifold theory gives us. And in particular, whether this picture that the genus of the worldsheet calculation is the genus of the covering surface materializes. Now the symmetric orbifold way of calculating correlation function for the dual CFT suggests that these correlators should be expressible in terms of the covering map. So the covering map has the property it maps zi equal to xi, and then it has a z minus zi to the wi if it has twist wi. Now, without going into all the details, there's one thing one can instantly understand that has to happen. You see, covering maps don't generically exist. Covering maps are a very special type of map, and they typically don't exist. So what do I mean by that? Suppose I specify zi and xi and wi for all of the n points. Then, in general, there will not be a covering map that will look like this near z equal to zi. Now, maybe this is not familiar to you, but there's one case that's very easy to understand. Suppose we consider the case n equals to 4, and we take the twists all to be equal to 1. Then we're looking at a 4-point function, and then the covering map, there's nothing special happening at z equal to zi. So actually the covering surface in that case is also a sphere, and therefore it must be a map from the sphere to a sphere, but a map from the sphere to the sphere is a Möbius transformation. So therefore, we are looking for a Möbius transformation mapping zi to xi, but for 4 points, generically, you can only do it if the cross ratio of the x's agree with the cross ratios of the z. So therefore, what we expect is that the correlation functions that correspond to a twist value 1 for fx, xi, and zi, they must be proportional to a delta function, namely they should only exist if the cross ratio of the x's equals the cross ratio of the z's. Now, this is a very unusual property for CFT correlation functions. I mean, this is not what your favorite CFT correlator looks like. You used to believe that CFT correlators are rational functions, hypergeometric functions, all of that. What we are claiming, or what we are proposing, or what has to be the case in order for this picture to work, is that this correlation function must actually have a delta function factor that localizes it to the special points where a covering map exists. Now, this seems very implausible, but we have a lot of control over these correlation functions. In particular, we can study the Ward identities, where we insert one of the SL2R currents here, and we look at this and use the OPE behavior of the currents with the spectrally flowed operators. Now, this is a bit subtle because of spectral flow, and this is quite complicated, but we worked this out very carefully. And what we found is that these Ward identities lead to very, very stringent conditions on the set of these correlation functions. And very remarkably, these very complicated constraints that we get on these correlation functions are solved by the answer that comes from the Lone Natur answer. I mean, this is highly non-trivial, in particular, including the delta function. So there are certain differential operators, and they're exactly solved, I mean, including this delta function piece, are exactly solved by the Ward identities that we derive from first principles. But it only works provided that k is equal to 1 and that all these spins are exactly equal to 1/2, which, as I said before, are the only representations that exist at k equals to 1 anyway. So this is, in my opinion, quite a remarkable result. It's really a first principles derivation that the correlation functions want to have this delta function behavior, which is what is necessary to reproduce the covering space, covering map picture. In particular, suggests that the worldsheet is really the covering surface of the dual CFT. Now, subsequently, this is a work that was done a few months ago. We used the fact that actually for the PSU 1,1/2 level 1 theory has a free field realization in terms of symplectic bosons and complex fermions. And there you can be a bit sharper. You can derive stronger Ward identities because you can not only just derive Ward identities for the SL2R currents, you can also derive Ward identities directly for the symplectic bosons and the complex fermions. And that allowed us to show that this delta function localized solution, i.e. this solution of this form, is in fact the only solution at k equals to 1. So there is no, this theory formulated in this manner, there's only one set of correlation functions, and it's exactly the ones that reproduce the Lunin-Matur answer and show that the worldsheet wants to be the covering surface of the dual CFT correlation function. And it's actually quite neat. There's a very quite elegant argument that smells a little bit like a twistor space description that shows that these correlation functions have to be 0 unless the covering map exists. And it hinges on this somewhat remarkable identity that really seems to suggest that you should think of these psi's as being the spinor variables in some twistor description of this background. Okay, so this is the second piece of evidence that this specific worldsheet theory that I proposed really gives you the symmetric orbifold of T4. I showed you that the spectrum is reproduced, and while we haven't shown that all correlation functions are reproduced, we've shown that the simple ones, the structure of them exactly matches the structure you would expect from the dual CFT. In particular, this covering map appears naturally, in some sense, out of the representation theory of the SL2R in the presence of these W spectrally flowed vertex operators. Now, in my final 10 minutes, or I don't know quite how much I have, I want to explain to you also our most recent work, which is going the opposite direction, explaining how you can see the string theory emerging from the CFT without knowing a priori what you should have looked for. Now, this works only in the large twist limit, but let me explain to you what we've managed to understand. So the Lunin-Matur answer written in some sort of compact form tells you that the correlation function of these twist fields is the sum over all the covering maps with some combinatorial factor, and then it's controlled by effectively this Liouville type action that gives you the conformal factor. And yeah, I don't want to get into the details of it. Now, the problem with solving it is that you have to find all the covering maps over which you have to sum. And finding covering maps is in general a very hard problem. So it seems very hard to start from here. So we were thinking of a way of finding a way of controlling this sum over the covering maps. Now, what we are going to concentrate on is the situation where the covering surface is again a sphere. So this is not the most general context, but that's applicable to a certain classes of correlators. There is a contribution from a sphere covering surface. Now, if the covering surface is a sphere, there's a simple formula. There's a simple formula in general, but that's the formula it takes if the covering surface is a sphere that tells you what the degree of the covering map is. So n is the degree of the covering map, and what this means is how many pre-images each point on the dual CFT twisted sector correlator, how many pre-images it has on the covering surface. So the covering map will be n to 1, where n is given by this number, capital N. Little n is the number of vertex operators, and wj's are their twists. Now, Pachmann, Rostelli, and Wasserman many years ago tried to find a Feynman type description of this covering map. And what they did is they looked at the twisted sector correlator on the sphere. They consider some Jordan curves that goes through all the points, through all the xi's, and in circles infinity ones. And then they lift this curve to the covering surface. And on the covering surface, this gives you closed faces. And each such closed face contains one point, which is the pre-image of infinity, because you went clockwise, say, around the infinity. So therefore, on the covering surface, the black dots are the dots that are mapped to infinity under the covering surface. So this is the picture for a 4-point function. So the green dots are the 4 critical points, the 4 insertion points downstairs. And W is 5, and therefore it's a 9-fold covering. So if you count correctly, you should see the 9 purple as faces. And I counted it the other day, and it is indeed 9. Okay, so this is for W equals to 5. And in general, it's very hard to find these covering maps. But our idea was that we should look at the limit of large twist, which is somehow the Gross-Mende type limit for this background. So we want to take the Wi as large, but we want to take them large in a uniform manner. So remember, the degree of the covering map is given in this way in terms of W. So we want to take all W's simultaneously large, such that the ratio W over N, which we call alpha, shall stay fixed. So this is a specific limiting type class of configuration where you're looking at correlation functions with higher and higher twists. Now, what can we say about the covering map in this context? Well, it's easy to see that the derivative of the covering map has to have this form. You see, the covering map has n poles, n simple poles, and therefore the derivative of the covering map must have n double poles. So these are the poles of the covering map. And on the other hand, near each of the critical points, it goes like wi, so the derivative will go like wi minus 1. And if you count the degree, you find that the derivative of gamma must have exactly this form. We've taken here one of the zi's to infinity, but none of the xi's to infinity, then you get this form for del gamma. Now, the actual covering map must have the property that del gamma doesn't have a simple pole, because you see, if you integrate del gamma to get gamma, you shouldn't pick up a logarithmic term. So therefore, if you look at this formula, at z equal to lambda a, the residue should be 0, and that translates into what Rumpetakis, who suggested that this is a good way of looking at this covering map, called the scattering equations. These are the equations that the lambda a's have to satisfy in order for del gamma not to have a simple pole and therefore really to come from an honest covering map. Now, the idea was to look at this scattering equation and think of it in the large n limit, with alpha being w over n being fixed, which is the limit we want to take, this Grossman type limit. Now, in that case, this scattering equation really looks like a matrix model equation, where this is the sort of the repulsion of eigenvalue term, and that's the term that comes from a potential, and the potential from which it comes is a Penner-like potential that is of this form, so that if you take a first derivative, you get just alpha over z minus zi. So this looks exactly like the equations that come from a matrix model in the large n limit.
What were the lambdas in
The lambdas are the positions of the poles of gamma.
Okay.
So remember, there are n poles because it's degree n. So these are the black dots. These are the lambdas, and they appear in the denominator of del gamma, and they appear here in the equation for the absence of the simple poles.
Okay.
Now, when you take n large, you can describe matrix model solutions by spectral curves. And what will happen is that these lambdas, you see, they're order n lambdas, and they will start to form little cuts. I mean, they will coalesce into cuts. And from the point of view of this picture, you see what will happen is in the larger limit, you only allowed to have a few big surfaces, and most surfaces will be small surfaces coming from just little loops connecting two vertices. So what you're going to get is all this infinity, or the preimages of infinity will form a cut, coalescing together, and the period integral around this cut will simply be the number of preimages you had here, or proportional to it, which is, roughly speaking, just the number, the ratio of big contractions between the ith vertex and the jth vertex relative to all the big contractions you have. So this is what the spectral curve of this matrix model will look like in the large n limit. And it's characterized by all of these different period integrals. It's characterized by specifying what ratio of contractions you have taken as you contract the different vertices of this graph. Now, quite remarkably, this spectral curve turns out to be equal to up to a prefactor to the Schwarzian derivative of the covering map. I mean, we have some elementary description. You have it in terms of W prime and the resolvent, and you can express this all in terms of the covering map data. And what you find is you get exactly the Schwarzian derivative, but the Schwarzian derivative defines for you a quadratic differential. So what this tells you is that the spectral curve defines for you a quadratic differential, and the quadratic differential has the property that all of these period integrals are real. Now, this is exactly what characterizes a Schroeder differential, and the different solutions, as you sum over all the Feynman diagrams, i.e., as you sum over all the covering maps, produces you all the possible Strabel differential for all possible values of these period integrals. But in turn, Strabel differentials are known to be in one-to-one correspondence with points on the string moduli space. So as you sum over all the covering maps, i.e., all the Feynman diagrams, you sum over all the Strabel differentials, and thereby you sum over the string moduli space. And therefore, what this shows you is that this correlation function is the integral over a string moduli space with a certain measure and a certain action, which you can read off from the original formula from which I started. This formula allows you to read off what the weight is with which any of these contributions appears in the string modular space. So this is a very concrete realization of this old idea of Rajesh-Gopal for how to reconstruct the worldsheet from super young Mills in that case. But here it works very similarly. You associate to this Feynman diagram Strebel differential, and as you sum over all the Feynman diagrams, you integrate over all the Strebel differential, and it turns into a modular integral from a dual string theory perspective with a specific action. And this action in this larger limit has the form that you can either think of it as a number Goto action in Strebel gauge, or it's actually equal to the modulus of the Schwarzian derivative. And that smells very like the ADS2 SYK type duality. So this is, in some sense, independent of what I said earlier, but it's a very nice way that shows that the symmetric orbifold correlators really fit into this general framework for how ADS-CFT duals should work. So I think I'm running out of time, so let me just wrap up. I've tried to convince you that the symmetric orbifold of T4 is really described by this worldsheet theory with one unit of NSNS flux. We showed that the spectrum and the correlators match. The worldsheet plays the role of the covering surface, and that suggests that duality can be made manifest in this manner. It also suggests that this will work to all order in 1 over n, not just to leading order in 1 over n, because the higher genus contributions produce indeed the sub-leading 1 over n contributions on the symmetric orbifold. This shows signs of a topological theory, only short representations, correlation functions localized to isolated points. Both sides are explicitly solvable, have free field realization, so this is really as solvable as it goes. This is something where we have both sides under total control, and we'll be able to understand everything we want to understand about this duality. And the last part is that I've tried to explain to you that this duality fits very naturally into the general framework of ADS-CFT duality, because the Strebel differential, which was one of the key players in this reconstruction idea, appears very naturally out of the sum over all the covering surfaces from the symmetric orbifold correlators. So for the future, we want to understand this worldsheet reconstruction in more detail. This is a very recent development. There are lots of open questions that arise in this context. We think this is really a topological string theory, and we want to make this more explicit. And then there are many steps in between. But eventually, we also hope that some of these ideas may actually generalize to ADS5, and that one should, by similar methods, be able to find the worldsheet theory that's dual to superangles in 4 dimensions, at least at a free point, which would then at least allow you, in principle, deforming from there to derive the ADS-CFT correspondence in the 4-dimensional case. Okay, thank you.
Thank you. Very nice. Questions? Emil, did you want to follow up on?
Well,
Amir also has a question.
Oh, Samir, go. Okay, why don't you? Well,
Stefano looks like
Samir, go for it. Samir, we can't hear you. You're muted.
Okay. So this was very nice. I mean, I'm just beginning to appreciate the full power of this connection between gravity and the CFT that you seem to have solved exactly. But let me ask, if just looking a little ahead, can you now, for example, get some of the results we had in the early days of work with fuzzballs? For example, if you take a CFT state at the orbifold point where all the n copies are bunched into circles of, let's say, length 2, then we know what the gravity dual of that is at the gravity point. And, you know, we have certain expectations of that and things like energy gaps and so on. And are there those kinds of questions now accessible with what you have done from now the gravity side?
In principle, yes. But I mean, the problem is that as our analysis shows, the string theory is at string length. I mean, the ADS space is at string length. So, I mean, we have a worldsheet, an explicit worldsheet description for every CFT state, but it's this level 1 worldsheet description. So it's very, very far from supergravity. It's, I mean, it's like when you try to describe string theory in S3, that you would think of as a geometric S3, but the analog is that our S3 is at level 1, where it's really equivalent to a circle. So our description is algebraically complete, if you wish, but it's very far from the geometry of ADS. You don't see the geometry of ADS directly.
I understand that. But remarkably, things like the kind of things which I mentioned, the travel time for this orbifolded gravity solution, there are some things which match exactly between the gravity point and the orbifold point. So there is something just nice about these things. It's not clear why they should work, but they do work.
I see.
So I was just mentioning those kinds of things. For example, energy gaps in these cases where every copy has the same orbifold number, they exactly match all the way between the supergravity point and the orbifold point. So those kinds of things might be maybe easy to access in your formalism.
Yeah, that would be interesting to look at. I mean, the problem for us will be how to translate from this worldsheet description to a supergravity description. I mean, you say you know the supergravity description that corresponds to a specific CFT state. We have a certain state in this representation of PSU 1,1/2 level 1. And it's not that obvious how to go from that description to something that you could directly write down in supergravity. But it would be interesting to see whether one can understand how this dictionary has to go. I mean, I agree with you that there must be something. So these are probably not BPS states, right? They are.
So these are still BPS states, and the point is you look for non-BPS excitations around those BPS states,
okay.
And you find certain energy spectra. Right. So around ADS3 itself, there's an energy spectrum of non-BPS excitations, but around those states which are quite far from ADS, but again, they also have a low energy spectra, but that exactly matches between the gravity and the orbifold point. So because there's so many magical things that match, including, as you know, the gray body factors and many black hole properties match, even the near extremal entropy matches between the orbifold point and the gravity point. So because there are so many magical things happening there, I was wondering if that's a direction that could be accessed by what you've done.
Might we surely look into it? I mean, I haven't looked into it, but it would be interesting. And it would be interesting to see whether one can see any connection between the supergravity solution and our description in terms of this worldsheet.
Sure. We can talk about it sometime.
Yeah. Okay. I think Stefano Masai was next. So, Stefano.
Thanks. Hi, Matthias. Just a quick question. So you had this proposal that for, at least for the continuous series sector of the strings for general K, it was captured by a symmetrical, an orbifold involving a Liouville factor. Is there any hope that these worldsheet reconstruction techniques work for that case, or is it too difficult?
You mean, sorry, which worldsheet reconstruction? I mean, at the last section or the...
Yeah, I mean, so you had this proposal that instead of having just D4, you had D4 times n equal to 4 Liouville. Yes. That should capture part of the continuous sector of the strings for general K, right? Yes. Can you start from this orbifold and try to apply these techniques?
Yeah, that's yeah. So that's that way I haven't thought about. Yeah, one could also try to do this. I mean, I should say this analysis largely depends on it being a symmetric orbifold. It doesn't depend so much on it what field theory it is. So certain, I mean, if you look at it, I mean, this has all to do with covering maps, and that's in some sense applicable to any symmetric orbifold theory. So a large of that program should also be applicable. Yeah.
Thanks.
Emil, I think you were next on the board.
Yeah. So the last part went by a little fast for me. So the matrix model that you're defining is, yeah. So what matrix model are you getting out? Does it change depending on the correlator you're looking at?
I guess so, yes. So I mean, this is the potential of the matrix model. So n is the number. So if you're looking at the endpoint function with twist wi, we are taking wi large, where wi over n is alpha. We keep alpha fixed, and the potential depends on the alphas and the number of points.
Okay. So
it's some sort of auxiliary matrix model that just helps you find the covering map. That's its purpose in life. It's not. I mean, it would be interesting to have a more microscopic interpretation for it. For us, it's at the moment just a way of solving these equations which characterize the covering.
Right, but I mean, usually one tries, when one encounters such a model, to come up with some sort of, you know, collective field theory of the eigenvalues or something of that sort. This is a one matrix model, or
Yes.
Yeah. So just wondering if there's.
Yeah, so I mean, this is very, very new, and there are many open questions, and it would be nice to have a more direct understanding where this matrix model comes from. That's not something we have seriously thought about, but that's a very good question.
Yeah. It seems like it's crying out for, you know, rewriting it in terms of some collective variables. Right, you're not going to want to deal with what's little n in that last.
Little n is the number of points in your correlator.
Ah, okay.
We should. Andrea wants to ask a question, and we should wrap up in 5 minutes. So, do you have a last quick question, Emil, or
no.
Okay, Andrea, over to you.
Just a quick question. What's the prospect of increasing the amount of an SNS flux?
I mean, this is similar to what Stefano asked. This is, I mean, certain things seem to work fine if you increase the amount of Neveu-Schwarz flux, but certain things don't quite work perfectly. So on the face of it, you can do lots also for larger K. So, but the first problem that happens is that this the continuum doesn't disappear anymore. So, I mean, this is specific to level 1. So if you're not at level 1, I mean, you can still do it, then you're going to get many representations. Also, the continuum will appear, and in some sense, that's responsible for the Liouville factor in the dual CFT. But you get also discrete representations. So in the usual NSR description, you know you have the continuum representations, these are basically these, and you have discrete representations. And in our case, it was only the continuous representations that survived, but if K is bigger than 1, you will also have discrete representations. And the discrete representations lead to somewhat complicated space-time spectrum. You have to solve this funny square root formula, and somehow we haven't really understood how this discrete part fits together with the symmetric orbifold of Liouville times T4. So somehow this only seems to work for the continuous part of the spectrum. So there are things we don't really understand, but there are certain things that work through quite analogously. So I wrote a paper with Lawrence Eberhardt in which we spelled out to which degree it works. Also, this localization formula for these correlators also works in a sense for larger K. So there's also a delta function localization for larger K, but it's not clear whether these are the only solutions. So there are various things that work similarly, but there are also things that don't quite work. So it would be very interesting to understand exactly what the status is if you do this for larger K.
I have an immensely naive question in the sense of, if you have K as 1, it's got this beautiful topological feel. It looks like the sort of ground states of a system.
Absolutely.
And if you have K as 2, is this something to do with the dynamics of 2 branes, which represent the 2 flux quanta, and then you've got all the motions, relative motions, or is there something?
Possibly. I mean, I probably something like that. I mean, it's surely very topological at K equals to 1, and that's somehow what you have to get in order to get just the discrete spectrum of the symmetric.
Right, but it looks very much like you're looking for ground states of some brane structure. You've got another, if your K is 2, sounds like you've got 2 branes, but then you've got the 2 ground state structures and then the interactions between. Which, anyway, it's really cool.
No, I think this,
Emil, if you can get it in 2 minutes, go for it.
Just sort of a blue sky question. Eventually one wants to perturb away from the symmetric orbifold point and, you know, get more towards the supergravity regime. So do you think that what you're doing, you know, will allow one to push towards correlation functions with large numbers of twists?
But large number of twists we've got now, right? I mean, that's what the last section is about.
Not large twist order. I mean, large, I guess, large little n. No.
Large number of insertions of
large numbers of insertions.
large number of insertions, I think, is not. I mean, I think so. From my perspective, I think the most pressing question in this context is that to switch on Ramond flux and see what happens when you go away from this somewhat special point.
Right.
To break the symmetric orbifold symmetry, and I mean, this is in principle what Berkowitz-Waffer-Witten set out to do, to start from this Wessel-Witten point and perturb it away and see to which extent one can get this under control. And
no, so you presented a simplification for a large twist order. I think what I'm asking is perturbing, is, you know, adding the marginal deformation that takes you away from the symmetric orbifold point.
Yes, I think this is exactly this perturbation. I think it's the perturbation that moves you away from the Wessel-Witten point in the hybrid formalism. So, I mean, there is the...
That's a different deformation, but...
That's also a descendant of a chiral primary, so that requires exciting away from the bare twist.
No, but I mean, here there's a term that switches on Ramond flux. So, I mean, I thought switching on Ramond flux is not exactly marginal in the... I mean, fundamentally speaking, you can't switch on Ramond flux. You can, because it's really discrete. So I think in this worldsheet theory, it doesn't appear as an exactly marginal operator, but it appears as a marginal operator. And I think there is an operator you can switch on that switches on Ramond flux, and I believe that's the operator that will perturb your way.
There are two senses of Ramond flux. There's the background Ramond flux of adding D5 branes to the NS5 brane background. There's also a Ramond flux, which is just the Ramond axion, which is the ground state of the twist 2, the Z2 twist operator.
Yes.
Ground state is a
Exactly.
modulus in this theory that turns on the Ramond axion.
Correct.
That's the thing which you have to turn on to perturb away from towards supergravity.
Right. So this is some marginal operator in this supergroup.
Yeah, it's condensing Z2 twists.
Right. So yeah, I have to.
I've always been confused about the sense in which what you're doing is there's sort of two senses of string interaction.
Hold on a sec. Let's continue this in the break, guys. Let's kill the recording and just thank Matthias and Emil. Then you can have at it. Okay. Thanks, guys, and we'll resume again in 23 minutes at 3:30. Thank you.